speaking on today is survival analysis. Sorry, my slides are not moving. Okay, and this is going to be the outline of my talk. We're going to look at understanding time to event data, understand the concept of censoring, what is conditional probability, what are Kaplan-Meier survival curves, how do we compare survival curves using the log rank test and the Harris. And finally, the choice of some oncological endpoints. So let's take the example of research in breast cancer. What are the different types of research outcomes that we can come across? I've tried to put this into a table. So for example, a researcher may want to know the proportion of patients who are HER2 positive. This is something we call categorical data because for each patient, the question we are asking is the patient positive or negative? Right? This is something called categorical or qualitative data. And you have a definite answer for each patient. Either she's positive or she's negative. Similarly, you may want to measure some levels, for example, estrogen levels. This becomes numerical data. How much is the level? Again, you have a value for each of your participants. But if you wanted to measure disease-free survival, this becomes time to event data. And the question is, at a particular time, did she have or did she not have an event? Let's go with a hypothetical research study. All the numbers are made up by me. They do not represent true numbers. So you're doing a study on breast conservation surgery, and you want to see what is the average time for local recurrence after surgery. You decide to do a study where for the next 8 months, all patients who undergo breast conservative treatment will enter your study, and you decide the study is going to end after 15 months, right? So patients enter the study at different time points depending on when they get operated. And so you have a total of 10 patients who have entered the study. All of them have undergone BCT, and you start following them up. So patient A, 8 months after surgery, has a recurrence. Patient B, 13 months after surgery, has a recurrence, and so on. And so you have a value for each of the patients. Now, these are the values. So I already told you A in 8 months, B in 13 months, and so on for each patient. And the average is 7 months. Can anyone tell me, is there a problem with this hypothetical example? Shubham, are they allowed to unmute themselves?
Ma'am, we don't encourage that because then we have a lot of speaking.
No problem. So we just go ahead. This hypothetical example is not going to work because in reality, what is going to happen is out of all the patients on your study, some are going to reach the end of the study without experiencing a recurrence. Similarly, some others will get followed up for a brief period of time and will then be lost to follow-up. So you can look at patient D and patient I who reached the end of the study period but did not experience the recurrence. Patient G was followed up for 5 months after surgery and was then lost to follow-up. So this is what the chart would actually look like. You would have numbers for some patients who had the recurrence, but for other patients, you would have incomplete data. How do you analyze this data? Do you exclude these patients, these 3 out of 10 patients? You can't do that because it will lead to loss of power or false results. Do you assume recurrence or no recurrence? Again, you can't do that, right? All you know is that for a particular time period after the surgery, the patient has not had a recurrence. To analyze this kind of data, we use something called survival analysis. Now, the word survival here is actually a misnomer, and it should preferably be called time to event analysis. The event could be death, it could be recurrence of disease, it could be progression of disease, it could be discharge from hospital. You could have non-oncological uses, for example, conception after infertility treatment. And the unique features of this type of data is that complete data is not available on all patients, either because of losses to follow up or because the study ends before the patient experiences the event, or the patient experiences another event which precludes the occurrence of this event. And the beauty of this kind of analysis is that we allow the patient to contribute to the study for the length of time he or she was followed up. We keep talking of event, and event means the outcome of interest. If you're looking at overall survival, the event is death. If you're looking at disease-free survival, the event is recurrence. If you're looking at progression-free survival, the event is progression of disease. The person who experiences the event is said to have had a failure, and the person who does not experience the event is a survivor. And actually, that's where the term survival comes from, somebody who has not experienced the event. Now, this is another term that you'll hear very, very frequently, censoring. And censoring means the value of an observation is only partly known. The most common type of censoring is what we call right censoring. What this means is that the patient enters the study, is followed up for some time, but we do not have information on the outcome of interest. And this is seen as a cutoff on the right side of the graph. For example, in this, patients D, G, and I all have entered. The timeline has moved towards the right, and then they've got censored. So this is examples of right censoring. Why do we have right censoring? First, patients could get lost to follow up. Second, study ends before the patient experiences the event. And lastly, the patient experiences another event which prevents him from experiencing this event. For example, if you're looking at time to death in dialysis patients, okay, and the patient goes and has a renal transplant, this is something called a competing risk, because now the transplant has changed his dynamics. He no longer needs dialysis. If you're looking at time to death in lung cancer patients, which is cancer-specific mortality, and the patient dies in a road traffic accident, now he has had another event which prevents him from having a recurrence of lung cancer or dying of lung cancer. So these kind of events will get right censored. Stopping briefly for any questions.
So now I realize why Madam was asking that you can ask questions in between, because actually, if anybody, you can put it in the chat box if you want to re-understand right censoring, because I thought I understood right censoring, but even I think after. So I have no questions on the Zoom link, Madam. You can go ahead. If they ask something, you can come back to that.
Sure. We go on to something slightly statistical.
So may I interrupt, ma'am? Is there something known as left censoring? Would there be something left censoring?
There is both left censoring and interval censoring. Left censoring, so we spoke about right censoring, which is you don't know about the outcome. Left censoring is when you don't know when a particular exposure has started. Let's take the example of HIV leading to full-blown AIDS, right? So we test somebody for HIV, and we know that on the day of the test, he is positive. But he may have been positive for months, years before that, unless he can give you a specific event which led to the positivity. Let's look at carcinomas in situ. You diagnose the CIS on the day that you test the patient, but unknown to you, the patient may have had CIS for many weeks, months before that. So what happens here is, when you're looking at when does CIS become more invasive, what you're actually looking at is, when does CIS from the date of diagnosis become more invasive? You don't know what happened on the left before the diagnosis of CIS. That's what is known as left censoring. However, unfortunately, there's no way of working around it, and so we don't see it reported in too many studies.
Okay.
Interval censoring is when you follow up patients at intervals. So you have a patient with cervical cancer and you call her for 6 monthly checkups. Now, at the first 6 monthly checkup, she's fine. At the second 6 monthly checkup, she's fine. But at the third, that is at 1.5 years, you find she has a new lesion. So when did this new lesion come? It was not there 6 months ago. It is there today. And it could have come any time during this interval of 6 months. And therefore, all you can do is note down what was the status at the previous follow-up, what is the status at this follow-up, but the period in between, you cannot pinpoint exactly when during the interval she developed that lesion or recurrence or whatever it is. And that's what is known as interval censoring. Unfortunately, left in interval, there's very little you can do about it because that's the nature of the study. You can't follow up patients or image patients every day. You have to accept that as one of the flaws of this method of analysis and just move on with it. There was a raised hand.
Yeah, so Dr. Bijan is asking that can you explain right censoring again? So I think if we can just go on to the graph and say, tell us, madam, which ones are the right censored ones?
Okay, so A, B, C are all patients who have entered the study, who have followed up, and who have had an event. So they have had a recurrence after breast cancer surgery.
So the red mark represents the event, right? The red circle represents the event.
These are all events. Patient D entered the study, got operated, was followed up for 12 months. So he got operated on this date. 12 months later, he has not yet had a recurrence. She has not yet had a recurrence, right? Now the study has to end because I can't keep continuing my study forever until this patient gets a recurrence, right? I don't know when she's going to get it. She may get it tomorrow. She may get it next year. She may get it after 20 years. She may never get it. So this is what is known as censored data, incomplete data. All we know is that this patient did not have a recurrence 12 months after her surgery. Beyond that, there is a cutoff. We have no more data on this patient. This patient got operated, came for regular follow-ups for 5 months. We know that until the 5th month, there was no recurrence. And then she decided to stop coming for follow-ups. So now, I don't want to exclude this patient completely from my analysis because I have some valuable information. I know that her disease-free interval is at least 5 months. I don't know anything beyond that. I don't know whether she had a recurrence here or after many, many years. And that is what right censoring means. When the patient enters the study, gives you some follow-up data, and then leaves the study before he or she has had the event of interest.
Okay. So, yes, ma'am, I think it explains it. So, there's a comment that, so when we say that we are right censoring, there is always a component of interval censoring as the follow-up is never continuous. You know, we call the patients at a 3 monthly frequency at the max. So yes. Obviously our data is collected at a 3 monthly interval. So we will always have a component of interval censoring in even a right censored patient, right?
Yes. Yes.
Okay. And madam, how do we account for competing event in the time to event analysis? Do we have to take them into account when we design the study itself, the competing event, like you explained about the dialysis? Those patients would be excluded from the study. I mean, those things would be...
No, so they would get censored when they have the competing event. Get it? So patient A did not die 2 years after he or she started dialysis. After 2 years, he had a transplant. And so now he is no longer available for analysis because he is no longer part of the study. But we know that in his case, the survival on dialysis is at least 2 years.
Okay, so we'll use that 2 years data.
In oncology, now that is an example of somebody who gets right censored 2 years into the study. In oncology, it becomes a little more tricky, okay? Particularly when you're looking at deaths. Because with our current reporting and even otherwise, it's very, very difficult to establish whether death was related to the cancer or not related to the cancer. For example, if a cancer patient dies of an MI or dies of a pulmonary embolism, we know that cancer causes thrombi, right? So is that death to be considered related or is it to be considered unrelated? Many patients die in the villages where we don't get data on how they died, what was their history before they died. And so looking at cause-specific mortality is next to impossible. All we do is we look at all-cause mortality. So their death due to other causes is not considered a competing risk. Okay. We just look at all-cause mortality. So we assume that if you're doing a two-arm study, the numbers of patients dying of completely unrelated causes like road traffic accidents will be equal between the two arms, and therefore you can afford to just look at all-cause mortality and solve the problem like that. Did that make sense?
Yeah. I think it finishes the question for this segment, madam. We can move on.
Right. So I'm going to start with something slightly statistical, and this is the concept of conditional probability. Okay. So if you toss a coin twice, what is the probability of getting heads both times? Okay. There are two ways of doing this. The probability of getting heads the first time is 1 in 2, right? You could get heads or tails, which is 50%. And the probability of getting heads the second time is again 1 in 2, which is 50%. Now let's look at the options that you could get when you tossed it twice. You could get heads and tails and heads, or tails and tails, which means your chances of actually getting heads and heads is 1 in 4, which is 25%, right? Which is nothing but the probability of getting heads the first time multiplied by the probability of getting heads the second time. So conditional probability is actually equal to 50% into 50%, which becomes 25% if you multiply it. Okay. This is how we calculate long-term survival. The probability of surviving 2 years after any disease is the probability of surviving the first year multiplied by the probability of surviving the second year. And the probability of surviving n number of years is P1 multiplied by P2, so on up to Pn. And it seems logical, right? Unless you survive the first year, you can't enter the second year. So you have to survive the first year, then you enter the next year, and then you enter the next year. And so the final conditional probability, it's called conditional because it depends on the condition that you survived the previous time interval. And that is what is known as conditional probability. We come back to this chart of ours, okay? You can see that each patient in this study has a different time to recurrence or a different time to censoring. So D, G, and I have time to censoring. And this is how I have rearranged it. I've started with the patient who had the shortest time to recurrence. Then I put in the patient who had the next time to censoring. So 5 plus means we know definitely that there was no event for 5 months. Beyond that, we have lost data on this patient, and so on. So I've arranged it in ascending order. Now we come to the important part, which is calculating the conditional probability. So we have the same graph over here, the table over here. You can follow whichever one you're more comfortable looking at. Now, when we do Kaplan-Meier survival, we don't use regular time intervals, okay? So the graphical method doesn't divide time into equal units. What it does is, it calculates time intervals depending on when patients have had events. For example, in this study, the patient shortest interval is 3 months. So after surgery, if 10 patients undergo surgery, one of them has a recurrence within 3 months. And so the first interval is taken as 0 to 3 months. What happens in this 0 to 3 months? You can see it here if you want. There are 10 patients who have had surgery, and at 3 months, one of them dies, right? So if 10 patients start an interval, one patient has an event, the proportion surviving this interval is 9, which is 9 out of 10, and that becomes 0.9. So in simple terms, this means 90% of patients who undergo surgery will survive to 3 months after surgery. The next events take place at 6 months after surgery. Please note that this censored is not taken as an event, but the next events are at 6 months. So the next time interval is 3 to 6 months. Now this person has already died, right? So he is out of the further analysis. We have 9 patients remaining for analysis. Out of these, this patient did not give us data at 6 months. And so this patient gets excluded from further analysis. Please note that this patient gave us data for the first 3 months. This patient told us that she is alive. And so we included her in this analysis. But when we're looking at the next time interval and at the end of the interval, we don't know whether this lady is alive or not. And so we exclude her. So we censor her during this interval. And at the end of the interval, we have 8 patients and 2 of them die. So the proportion surviving this interval is 6 out of 8. Okay, because 2 have died, which is 75% or 0.75. And here the concept of conditional probability comes in. Therefore, the conditional probability of surviving from 0 to 6 months is 90% multiplied by 75%, which is 67.5%. So 67.5% of patients who undergo surgery will survive to the 6th month after surgery. Now, normally I make this interactive and ask people what the next interval will be, but I guess that option is not there today. So let me tell you that the next interval will be when the next events take place, and that is at 8 months after surgery. Okay. Again, censored, so we don't count a time interval over here. We go straight to the next events, which is at 8 months. So 4 people are already out of our study at this time point, right? 3 have died and 1 got censored earlier itself. Again, here 1 is getting censored. So let's look at that table. Between 6 to 8 months, we started with 6. 1 got censored. 5 survived to the end of the interval. Of them, 3 had events. And so the survival probability is 2 by 5, which is 0.4. And the conditional probability of surviving this entire time interval from 0 to 8 months is previous probability multiplied by this probability, which is 0.27. And so it goes on. You don't need to do this manually. This was just for your understanding. Any statistical software will do this for you, provided you have a date of starting, which could be date of randomization or date of surgery or date of, whatever, diagnosis. You have an end date, which is the date of follow-up, and you have a status at follow-up. Is it event or no event? It will automatically draw up this graph, and it will automatically censor and do this entire process for you. Now coming to the actual Kaplan-Meier survival curve. Okay, so on this curve, time is represented on the x-axis and survival probability on the y-axis, right? Now remember, when we start at time 0, everyone's alive because that's when the study has just started, right? So if you have 100 patients starting, they may have entered the study at different time points, but for all of them, their time point of starting is time 0. The table is down here. We just derived that table on the previous slide. You can see that if everybody is alive initially, then at 3 months, survival probability drops to 90%. At 6 months, it drops to 67.5%. At 8 months, it drops further. And then it comes down to baseline because all the patients on the study have either died or got censored. If this last patient had not died, this line would not have come to the baseline but would have continued like this. Censored patients are depicted as vertical ticks. So you can see 1 patient got censored 5 months after her surgery, 1 at 7 months after her surgery, and 1 at 12 months after her surgery. Now, this was a really small study with 10 patients, which is why you can see all these steps so clearly. If you do a study with 25 patients, so the study started with 25 patients, obviously you're going to have more events, right? And you can see that the number of steps is more. And when your study runs into hundreds of patients, these little steps actually combine to take the form of a curve, okay? And that's why it's called a Kaplan-Meier survival curve, but actually it's not a curve. If you were to magnify this, you would see that it's a series of little steps going down like that. Each downward step represents an event or events, depending on how many patients have had the event at that time. I spoke about how we show censored patients as vertical ticks. With so many numbers, we can't show that, right? So they show the number at risk over here below the graph. Okay, and you can see as you move towards the right of the curve, the numbers will keep decreasing, and that's because within 12 months, many got censored and many had events. 24 months, more got censored, more had events. And so the numbers at risk will keep decreasing as you go towards the right. Now, when you go towards this right, your data becomes more and more unreliable simply because your numbers have become really, really small. And in statistics, we know that when our sample becomes really small, data becomes less reliable. So be very, very careful while interpreting data on the extreme right of a survival curve because your numbers at risk are going to be really small over there. Even if you didn't understand any of that, it's fine. You need to know how to read a curve, right? We already spoke about how time is on the x-axis, survival probability is on the y-axis. Now, I may be interested in knowing what is median survival, right? Median survival is when survival probability is 50%. We know that median means the 50th percentile. So you draw a horizontal line at 50% or 0.5 and see where it meets the graph. So you can see that in this study, median survival is roughly 6 months. Some studies may not have had events. For example, the graph will be hovering somewhere here. You cannot talk about median survival because the survival has not reached 50% probability and not enough patients have had events. On the other hand, you may want some time-specific survival. For example, you may be interested in 1 year survival. So what proportion of patients are likely to survive 1 year after a particular treatment? You drop a vertical line at 1 year and see where it meets the graph. And it's roughly maybe 27, 28% in this case. So that's the 1 year survival. So this is how to read median survival and time-specific survival on a Kaplan-Meier survival curve. Remember, curves which crash down, come down rapidly means more events are taking place. Curves which hang up here are very, very slow, which are sort of plateaued over here, means events are not taking place. Stopping for questions?
So Dr. Kundu has asked that does censoring has anything to do with the intention to treat and per protocol analysis sites?
Not really. So intention to treat means that we include all patients in the final analysis, irrespective of what treatment they actually received. So supposing you received randomize somebody. So suppose there's a study with 2 arms. One is chemotherapy followed by surgery and the other is surgery alone. And a patient was randomized to the surgery arm, but for some reason ended up getting chemotherapy. You would still analyze that patient in the surgery arm, okay, as if he had received only surgery. And the reason for this is to minimize bias and to mimic a real life scenario. On the other hand, per protocol analysis is where you only analyze those patients who have adhered to the complete protocol. So if somebody was randomized to surgery and he went into chemotherapy, you would take him out of the final analysis. Both have their pluses and minuses. Per protocol gives you the ideal effect of the study intervention. However, it is not what is going to happen in real life, and so it doesn't mimic the real life scenario. ITG helps to minimize bias, but it can lead to problems if there are lots of these kind of patients violating the protocol. Okay, further discussion is not really in the scope of this topic.
Dr. Aradhya is asking why the intervals are not equal.
Yeah, that's a good question, and So the reason for that is that's how it is done in something else, which is known as life table analysis, and that's how our insurance policy makers calculate the premium. Okay, why is it not done in equal intervals? It's not done in equal intervals because supposing I chose a 1 year interval, okay, and I wanted to know how many patients died during this interval. Now, this person died at 7 months, at 6 months, right? You can see the step down. So, would you consider him dead or alive for this interval, for the 1 year interval? So, it becomes difficult, right? Or you would have to put in a very complicated calculation and count him as alive for half the interval and then count him as dead for the remaining half of the interval. 6 months is still easy because it's half and half. But supposing somebody dies at 7 months or 8 months or 9 months, right? How do you account for them in a 1 year survival period? So you say that he was alive for 9 out of 12 months and then he died for the remaining 3 months. So the calculation of time-based survival becomes difficult because when somebody has an event in the middle of that interval, you don't know whether to take them into account as alive or dead. This becomes less of a problem when you're doing large population-based studies, which is what the census and all do when you're doing millions of patients. But when you're doing 200, 300 patient studies, this becomes a problem. And that is why Kaplan-Meier is a product limit. So instead of taking equal intervals, it takes intervals when there are events so that you clearly know at this particular time point, X has died. And therefore, before this, he was alive. And after this, he is dead.
Okay, so the intervals are driven by events and not a time frame as such.
Completely. Events in Kaplan-Meier method are totally driven by events, when events take place. So that is why you will have very unequal intervals. So initially, you will have a lot of small intervals because events are more and more frequent. But as patients sort of have good long-term survival, when you move on in your study, your events will become fewer and your time intervals may become larger and larger.
So Dr. Aradhya has asked again that how is it decided by how many events? I think the event word has to be described, madam. That what is an event?
Okay, the event is your outcome of interest. So if you're looking at overall survival, then death becomes your event of interest. If you're looking at recurrence-free survival or progression-free survival, then recurrence becomes your event or progression of disease becomes your event. The reason is Kaplan-Meier is the more accurate way of doing it, Aradhya. If possible, you should do only Kaplan-Meier. But when you're looking at large populations, okay, what they do is they rely on the census, how many were alive this year and how many were alive after 5 years. And it's not possible for them to capture data of exactly when each patient died. Okay, I'm not talking about population-based oncological studies. I'm talking about in general population-based government data when they do the census and capture deaths, and so there they sort of approximate and use these kind of fixed time intervals. Okay, but ideally, wherever possible, you must use Kaplan-Meier because you know the exact time point when people have died.
Is there a minimum sample size to draw a Kaplan-Meier curve?
So the sample size depends on what you're studying, how many events you expect, and how early you expect those events. So there is a way of calculating sample size for a Kaplan-Meier curve as well, depending on the expected probability of events. But there's nothing to say that you should have 10 or you should have 20, except that the more you have, obviously more reliable your data is going to be.
Also, it will be more a curve like if you have more sample size rather than waterfall. Have more events, more subjects means more events probably, and then probably a more smoother curve. Is that so?
It's not really like that. Okay, so if I have say 10 subjects in my study, okay, and one of them dies, okay, that changes my survival probability by 10%, right? From 100, from 10, it's come down to 9. Now, assume I have made a mistake in categorizing this patient. Okay, instead of dead, I've coded him alive, or instead of alive, I've coded him in dead. I'm creating a 10% mistake in my data analysis, okay, because of one person. Now, imagine if I have 100 people in my study and one person's data is coded wrongly. It will cause only a 1% change in my analysis, because whether he's dead or alive is 1 out of 100. If I have 1,000 patients, it's a 0.1% mistake, right? And so the validity of Kaplan Meier curve increases as the sample size increases. Obviously, this doesn't mean you can do infinitely large samples for every study. So you need to sit with a statistician, tell them the expected number of events. Okay, so what is your expected to your survival? If you're looking at prostate cancer, you will need a much longer follow-up because your events don't happen so easily. People don't die, they live for many, many years. If you're looking at lung cancer, probably a shorter follow-up, and you're expecting more events to occur in the first couple of years, right? So it depends a lot on the biology of the tumor, how aggressive is the tumor, how toxic is your treatment, and when events are likely to.
So do the horizontal lines have any significance in the graph? So we saw the vertical drops, but the horizontal ones,
actually mean nothing is happening. Nobody is having an event. Okay. And then if there are ticks here, it means people are getting censored. So here nobody is having an event, and then event, no event, event, no event, event. Obviously, people might be getting censored over here. So if this final thing, for example, here, between 110 months and between 170 months, there were no events at all.
Okay. There's another question on sample size. How to calculate expected events needed for sample size estimation?
So you actually have to calculate the hazard ratio, and I'm going to be coming to that in another 5 minutes or so. So please bear with me.
Okay, so we'll take this question at that time. Dr. Goyal has commented that rare diseases have small databases and survival graph would be step-like. So this is commenting on the one thing that I said, that it would be a smoother curve with larger number of patients. So yes, ma'am, we can move. Yeah. Okay, ma'am, we can move on.
Okay. Now we come to comparing time to event data. So far we saw how to draw a survival curve. Sometimes you're comparing two treatments, right? And you want to know, is the time to event data different between these two treatments or interventions? So I've taken this example from NEJM 2019. This was a trial which looked at overall survival with fulvestrant plus anastrozole versus only anastrozole in metastatic breast cancer. And you can see here that the anastrozole arm had 247 deaths, okay, out of a total of 349 patients. And the control arm had 261 deaths out of 345 patients. Okay. And you can see what I told you, as you go down, the numbers at risk have gone down, 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 okay, because a lot of patients have had events and probably some have got censored as well. The log rank test is what is used to compare the number of events in the two groups. So it tells you, is there a difference in the total number of events in group A versus group B? The problem with the log rank test is it is not time sensitive. So supposing group A had a lot of events over here, okay, and group B had a lot of events over here. Finally, the total number of events would be the equal. But it is not picking up the fact that people in this arm have died earlier than people in that arm, which is why those studies report the log rank test. It is not considered a very sensitive test, and it is not the preferred test. What is preferred is something called a hazard ratio. The hazard is the opposite of survival. So far, we were talking about survival, right? Not experiencing the event, not experiencing death, not having a recurrence, not having progression. Now we are turning the table and asking the reverse question. So on this study or in real life, at any given time point, what is the risk of death in a person receiving combination versus receiving single agent? Hazard ratio compares the risk in the two groups. It's somewhat similar to relative risk, except that it calculates risk at any given point of time during the curve. Okay? And it tells you at any given point of time what is the risk of the event occurring in one group versus the other group. For example, in this study, they said the hazard ratio for combination is 0.82. What this means is that if you take the single agent arm to have a risk of 1, then the hazard for the combination is 0.82, which means there is a reduction in the risk of death. They also give you 95% confidence intervals as 0.69 to 0.98. When I tell you that the hazard ratio is 0.82, what it means is that the combination reduces the risk of death by 18% because 1 minus 0.82 is 0.18, which is 18%. So in this study, the use of combination therapy has reduced the hazard, has reduced the risk of death by 18%, which is significant, right? Shubham, do I need to cover the concept of confidence intervals or has that been done already?
No, it's not been done, madam. You can please.
So this is our study result. Confidence intervals tell us if you were to repeat this study in the population, what are you likely to find? Because we know that results of a study, when applied to a larger population, may not remain exactly the same. And so the 95% confidence intervals for this hazard ratio are 0.69 to 0.98. What this means is that in this study, the risk is 0.82. In the population, you can be 95% confident that the risk could lie anywhere between 0.69 to 0.98. What this further means is in this study, it reduces the risk by 18%. In the population, it could reduce the risk by as much as 31% or as little as 2%. But there is some risk reduction. The magnitude of the risk of death, the reduction of risk of death, varies between 2% and 31%. This is a difficult concept to understand, and if you all want, I'm very happy to go over it once again.
Yeah, please do, madam, and also explain how does a wider confidence interval and a narrower confidence interval gives us about the importance of study or the designing of study.
So, confidence intervals depend on something called the standard error. This is a very statistical term. What a standard error tells you is how much is your study result likely to be different from the true population finding, right? And it depends on two things. It depends on the variability within your study, and more importantly, it depends on sample size. I do not have slides on this because this is not really hardcore survival analysis. This is true of any statistical test, whether you're talking about an odds ratio, a risk ratio, a relative risk, or a hazard ratio. Okay, you could even have confidence intervals for means or proportions. A confidence interval gives you the range of values that you could expect to see in the population. Confidence, the width of the confidence interval is inversely proportional to the sample size. So the larger your sample, the narrower your confidence intervals are going to be. If you have a small sample size, your confidence intervals are going to be very wide. And that is why when you asked me what happens when you have 10 patients in a study, you may get a study result, but the confidence intervals are going to be very, very wide. And therefore, you cannot reliably tell people that this is what I'm expecting. For example, imagine that you were to start using this new therapy in your patients, right? This combination therapy. What would you tell them? I read one paper where your risk of death reduced by 18%. However, I'm not sure. It could reduce by only 2%, or it could reduce by as much as 31%. Now, imagine that this combination is very toxic or very expensive. How would the patient or you make an informed decision? Because if the benefit is a 2% risk reduction, is it worth taking it? If the benefit is a 31% risk reduction, it's definitely worth taking it, right? Which is why studies with wide confidence intervals do not inspire us to change therapy, because we know that the true effect could lie anywhere between these two values. And that is why when we calculate sample size, we sit with the statistician and tell them what do we expect the level of confidence to be, okay? And then they calculate the sample size so that you will at least try to get reasonable confidence intervals. That may not happen, but a study should at least attempt to have enough sample size to have reasonable confidence. Did that answer the question, Shiva?
Yes, madam, it did. So, Dr. Aradhya is asking, is there a relationship between confidence interval and hazard ratio?
A confidence interval is the boundary around the hazard ratio. Any study statistic, odds ratio, relative risk, hazard ratio, mean, proportion, any study statistic will have confidence intervals built around it. Confidence intervals just tell you, for this particular study, this is the result, but what is the spectrum of results I can expect to see in the population 95% of the time. Remember, you can never be 100% confident. There's going to be some variability, but you could have 95 or 99% confidence intervals. So every such statistic is reported along with confidence intervals so that you know the magnitude or the spectrum of variability that you're likely to see in the population. So confidence interval is not exactly related to hazard ratio. It is reported along with every study summary statistic.
Okay, ma'am. Ma'am, I think let's move on with the survival analysis because now we are getting questions on relative risk and hazard ratio. And
We'll take all the questions at the end which are not related to survival analysis.
Sure. Thank you, ma'am.
Okay, this is something like a forest plot that we do. So a typical forest plot is done for a meta-analysis. That is a completely different topic. We are not going there. This is the line of unity. Okay, the line of unity means your hazard ratio is 1 and there is no difference between two treatment arms, right? So if hazard A divided by hazard B, if risk A divided by risk B is 1, it means that the two risks are equal. Now, for this study, we know that overall, the hazard ratio was 0.8, which means that A plus F combination was better. And the confidence intervals are shown over here. Okay. You could do subgroup analysis for different age groups, disease sites. You could choose your subgroups and calculate independent hazard ratios for each. For example, in the age group of people more than 65 years, how effective was this combination as compared to single agent? In non-visceral disease side, how significant was this combination or how effective was this combination as compared to the single agent? There's something that I did not cover when I spoke about confidence intervals, and I'm going to mention it now. If confidence intervals for a ratio cross 1, okay, you have a problem over there. For example, look at this confidence interval, okay? In this study, in non-visceral disease, the hazard ratio was 0.88, which means in this study, there was a 12% risk reduction in this group. However, the confidence intervals are 0.64 to 1.21. What this means is that in the population, the combination treatment could either reduce the risk by 36% or actually increase the risk by 21%. This is not statistically significant because you're no longer sure that the combination is better than the single agent because there is a probability that the combination could actually increase the risk. So if your ratios, odds, relative risk, or hazard ratio, if the confidence intervals include the value 1, it means the result is not statistically significant, and it means that the new therapy could either be worse or be better than the standard therapy. Now, there's one big assumption when we are making when we calculate hazard ratio, right? We are assuming something called proportional hazards. And what this means is that though the actual risk of death is changing with time, so we know that initially the risk of death is more, but as people have long-term survival, the risk of death keeps decreasing. And that is why this curve, which is initially a bit steep, is slowly starting to flatten out. We're assuming that though this risk is actually changing over time, the ratio of hazard in treatment A versus treatment B is remaining more or less constant, which means one treatment arm is always having a slightly higher risk than the other treatment arm, right? It could be 2 versus 1, it could be 1 versus 0.5, it could be 0.5 versus 0.25, but the ratio is remaining more or less constant. What the statistical software does is it calculates the hazards in both these arms at multiple, almost infinite time points and averages out a hazard ratio. Sometimes this may not happen. The hazards may not remain proportional. Okay, let me show you an example. This was from a Dutch gastric cancer study. I can't remember what the two arms were. I think it was D1 versus D2 dissection. You can see that one arm initially had a worse outcome. So here, this blue is having a better survival as compared to the red, right? And at some time point, it crosses over. And now actually red starts doing better than blue. Now, if you were to calculate a single hazard ratio for this, you would miss this point, right? You would miss this difference because it would give you a hazard ratio of 1. And they actually did that. Okay, they calculated a hazard ratio and they got a hazard ratio of 1 for this simply because here one was better than the other and here the other was better than this. So when you have curves which are non-proportional, you cannot calculate a single hazard ratio. This needs a very complicated analysis. You need to sit with the statistician and work out something which is time sensitive. So what you'll need to do is say at this time point, calculate, sort of divide the data and say for the initial part, this is the hazard ratio. And then for the subsequent part, it actually reverses and this is the hazard ratio. And of course, you need to have a biological, plausible reason why this is happening. Is it that immediate morbidity is more or long-term survival is better? I don't understand so much of the science behind it, but it needs to be scientifically plausible. Stopping for questions?
Okay, so I think Dr. Geeta had one. Dr. Geeta, you want to comment?
Unmute myself.
Yeah.
So I'm learning so much. So I'm just trying to figure out. So when you test a drug, so you don't know the new drug. How do you fix the number of events when you're looking at a new drug and testing it against the standard of care? And lots of times you see, you will have a study where the number of events that you were expecting don't happen. So when they don't happen, does it become a negative study or how does it work?
It doesn't become a negative study. So it becomes a study which was underpowered to detect the difference that you wanted to detect. Because when you have smaller number of events, you actually need larger number of patients, right? So the study will be a negative study, but that's not always a bad thing. The second thing is, how do you know the number of events? So I just spoke to you about hazard ratios, right? You need a pilot study, an early phase study, a phase 2 study, have a guess about how much of risk reduction would you expect with the new drug. And based on that, the statistician will calculate the sample size and tell you the X number of expectation of 40% of your patients to have events, and therefore to have number of events, you need Y number of. Okay, and because you do say 100% a year, your Y patients will get accrued over 5 years, and you need to follow them up for so much more time to ensure that enough people have events. And this is a pretty common problem what you brought up. We always tend to overestimate our accrual capacity. We always tend to exaggerate the expected difference, and so a lot of studies will at the end not have enough events. But either you can amend the protocol and change the sample size depending on what you're seeing, or that will form the basis for a bigger, better study.
My only concern is, suppose there is a new drug which probably has the potential that you're looking at, but because of poor accrual, you tend to shelve that study and you probably don't get the right answers and you probably just, that drug goes off your table. So
that is a very real problem, and which is why the choice of endpoint has to be really carefully done so that you do get enough endpoints, events. For example, in a prostate cancer study, if you're going to be looking at overall survival, you know that you're not going to have so many deaths. So there, probably you need to change your endpoint and use some surrogate endpoints. Okay, levels
Right.
of we can just probably use depression, and I'm going to cover oncological outcomes in a couple of slides.
Sure. Thank you.
Okay, so Dr. Jagdish is asking, why do we need to calculate the proportional hazard ratio? I mean, do we actually take it into consideration, or we just get away by creating a KM plot?
You can create a KM plot, but a KM plot won't actually tell you a quantitative number for the difference. Okay, and risk is something people like to know. So so you could tell somebody that so if you were taking these two drugs or versus this one drug, your 5-year survival would improve to say 28% versus 24%. That's one way of putting it, which is okay. But people are more interested in knowing what is my risk of death, what is my risk of recurrence. And so hazard ratio quantifies the risk of experiencing the event.
Okay, so madam, when we say risk, I mean risk we always associated with death. I think risk is to be for the occurrence of that event, right? It might not be death.
You hit it spot on. Remember, survival analysis is not always about death. Though we talk about survival, it's about surviving the event, and the event could be anything. The event could be recurrence, the event could be progression, the event could be anything, not just death. So when we say risk, we mean risk of having the event, depending on how you have defined the event.
There's one more question, madam, that is this appropriate to estimate disease-free survival, overall survival when the event of interest is less? And you can actually have more events if you increase the study period. So, I mean, I think it's again to do with having less number of events with the
Sure.
study.
Okay. Can I answer that question when
Yeah,
I...
Okay, survival we'll take. Sure, ma'am, sure. Dr. Tapas from Vishakhapatnam is asking how can we compare the OS and PFS between two arms at 1-2 years to arrive at a p value whether significant or not. I think, ma'am, we'll move on to the survival ones then.
That's fine. I can take that question here because I'm not really
Sure.
part again. So what they would do is they would calculate the 2-year survival in this arm versus the 2-year survival in this arm. Okay, they would calculate the difference and they would run a test and tell you whether it's statistically significant or not and give you confidence intervals for that difference. So maybe here the difference is about 2 months or 3 months. I don't know. It's not very visible from this curve. But a statistician will tell you that the 2-year survival, the difference was 3 months between the two groups. The confidence intervals are 4 months to 6 months or whatever. And the p-value is so much. So that's how you would compare time-based survival between two treatment arms.
Okay.
Because I'm realizing it's close to 9:30.
Sure, ma'am, but I think everybody's enjoying it. We have almost a full. I'm not sure how much time you have because.
That's fine.
Okay. So, ma'am, we can move on.
Choosing endpoints in trials with time to event outcomes, right? This is a very, very useful reference, though it's meant for industry, but the definitions are very beautiful over here. It's a US FDA download and it's freely available. This is another very useful resource, the National Cancer Institute. So if you go to their website, they have a dictionary of cancer terms. And when you click on it, you get the exact definition of each of the terms. Let's look at some of the outcomes which are commonly used in oncology studies. Now I'm going to paraphrase Professor Ian Tannock from Princess Margaret. He's a well-known oncologist, and this is what he has to say. He says there are essentially only 2 ways in which patients may benefit from oncological treatments. Either they live longer or they live better. Which means if you're running a large phase 3 trial, your endpoint has to be overall survival with or without quality of life to show that somebody is living longer and in the time that he's living longer, he's also living better, because there's no point in prolonging life if that life is going to be a miserable life. Any other endpoint that you use is a surrogate endpoint, and you should show that this surrogate endpoint can predict overall survival or quality of life. So overall survival is defined as the date of diagnosis or the date of randomization or the date of start of treatment to death from any cause. Okay, it's all cause mortality. We already spoke about how it's impossible to get cancer specific mortality, and therefore for the purpose of convenience we take all cause mortality, which is overall survival. So here your event of interest is death. The strengths and limitations of using overall survival: it's a very precise measure. It's an objective endpoint, right? You can either be dead or you can be alive. There's no in between. So it's less susceptible to bias. The problem, as we've already discussed, is that in some conditions, the typical length of survival makes OS an impractical outcome, right? So prostate cancers or breast cancers, where your follow-up is likely to be very long and your events are likely to be very less, using OS becomes a problem. Another term which is very frequently used is DFS, disease-free survival. This is defined as the time to the development of new disease or death following complete radiological resolution of tumor after curative treatment, which could be surgery, radiotherapy, or chemoradiotherapy. And this is mostly used in the adjuvant setting. Okay, so patients had curative treatment, you know there's no disease, and now adjuvant therapy is being tested. So here we talk about disease-free survival. Event-free survival is the time from randomization or start of the study to any of the following events: progression of disease that precludes surgery, if you're talking about the neoadjuvant setting, local or distant recurrence or death due to any cause. And event-free survival is usually used in the neoadjuvant setting, and that's because the patient has disease. So you can't really talk about a disease-free survival because he's never disease-free, right? So the patient has disease, and so you prefer to use the term event-free survival. Progression-free survival is defined as time to progression of existing lesions or development of a new lesion. Okay? And this is used in the locally advanced or more commonly in the metastatic setting. So when you have somebody with metastatic disease and you're monitoring for worsening of that disease, you would talk about PFS, which is progression-free survival. Another term is time to progression. Now, the difference between time to progression and PFS is that time to progression does not include deaths. In oncology studies, this becomes a problem because we are never sure whether death was related to the cancer or not. And so time to progression is not a preferred endpoint. If you're looking at metastatic patients, you should be using PFS. The strengths of these endpoints, PFS, DFS, EFS, are they typically require less time to observe as compared to OS, right? But the limitations are you need to have very standard definitions. There are some concerns that, DFS, so patients may not be really disease-free if there is micro disease. Second, is progression or recurrence really important to patients? So do patients really care about the length of their life or the length of their life without disease? Okay? And there are examples where PFS and DFS have not predicted OS. Again, to quote Ian Tannock, this was a study looking at various treatments for breast cancer. I'm not going into the science of it, but you can see on the left, the graph is a PFS graph, and you can see that this treatment seems significantly better than this treatment, right? Hazard ratio of 0.36, which means an almost 70% decrease in the risk of progression. But it translated into no difference in overall survival. Here you can see the 95% confidence intervals have crossed unity, which means that the new therapy would actually worsen the risk of death. If you go to the FDA website, you will have examples of conditions in which they accept PFS and DFS as surrogates for OS. And then they'll give you examples of where you cannot be using PFS and DFS instead of OS. I didn't have the time to include that over here, but you can look it up. These are again terms which are used sometimes: recurrence and relapse-free survival. So recurrence-free survival is just a synonym for disease-free survival. Relapse-free survival includes recurrence but doesn't include death. So this is like time to progression, which includes progression but doesn't include death. So relapse-free survival again is not a preferred oncological term. And then we have objective response rate, also known as overall response rate. So it's defined as the proportion of patients who have an objective response obtained by treatment of the tumor. And I think you all know there are standard criteria, RECIST criteria, and other criteria for defining what is a response, partial response, complete response. Any questions?
So many of these terms were actually self-explanatory, but I may ask, nobody has put a question, but I may ask, for a metastatic setting, many times we feel that OS is not a good marker, and people tend to use PFS as a better marker for assessing intervention.
Yeah, which is not unreasonable. You could use PFS as a marker, and ideally combine PFS with the quality of life indicator to show that the increase in time in the progression-free survival was also accompanied by a better quality of life. It's not unreasonable.
So the reason why I asked is because when I looked into why OS is not used, because they said whenever the patient has a progression, they cross over to the other arm, and that is why they can not reliably choose OS as the correct indicator, and only a PFS would indicate better treatment outcomes rather than a OS.
Yes, and this happens in adjuvant therapies also when we're talking about disease-free survival, because when the patient has a recurrence, sometimes they cross over or they receive other therapies which may prolong their life after that, but is not directly related to your intervention in question. And so when you have something like that, OS does not truly represent the effect of the intervention, and therefore DFS and PFS should be used. Many studies will report both OS and DFS or PFS as a secondary endpoint. You could have PFS or DFS as a primary endpoint in selected settings and also report OS.
Okay, Dr. Tapas is saying that many times we don't have a radiological documentation of disease-free. So can we consider clinical disease-free as a calculator of DFS rather than having a radiological?
Okay, I am not an oncologist, I'm an anesthetist, so I really don't know how to answer that question. I suppose if it's built into your protocol and both arms are being assessed in the same way, it should be okay. It's just that it should be standard, is my understanding. But honestly, Tapas, I'm an anesthetist, so I don't really know about this.
Okay, and should we directly consider the date of treatment completion to date of recurrence for DFS calculation? So how do we define the disease-free survival?
Yeah, so date of randomization is a better way, because if you have two treatments, one which is going on for a longer time and one which is a very short treatment, then if you take date of treatment completion, you're actually shortening the DFS, right? Particularly if you're comparing observation versus some treatment, and your treatment is going to go on for 4 months, 6 months, then date of completion of treatment has already taken away 6 months. So ideally, date of randomization is available.
And if it's not a randomized trial, then probably date of enrollment into the study or something?
With a single arm study, then it doesn't make a difference. If you're just doing an observational database, it doesn't make a difference, provided you report it like that.
Okay. So uniform reporting, basically.
Uniform reporting. So if you report that we calculated disease-free survival as date from ending treatment to date of documented disease, that should be okay.
And we can move forward. Okay, so there's one. Okay, no, we can move forward.
Just a couple of quick slides on length of follow-up. How long should you follow up your patients? Obviously, you need sufficient follow-up to capture enough events so that you can run appropriate statistical tests. Otherwise, as we discussed, your study is going to be underpowered. And this would be based primarily on the severity of the disease, okay, and on the prognosis of the participants. So obviously, in the palliative setting, you don't need very long follow-ups. But in cases like prostate or breast, you do need. Just an example, for a lung cancer trial, a 5-year follow-up would give you more than enough events, but for prostate or breast, it may not be adequate. And you need to report how long your patients were followed up so that readers understand whether the follow-up was adequate to capture events. Okay, there are various ways of doing it. One is to report the median duration of follow-up of all subjects. This includes those who had events and those who got censored. Okay, but now supposing your subjects have all had events very, very quickly, then this doesn't really represent the true median duration because it will shorten the duration. The other way of doing it is to do something called median duration of follow-up of censored subjects. So how much data did you get on your censored subjects? How long were they followed up before you had to end the study or before they were lost to follow? And the last is something called a reverse Kaplan-Meier technique, which is supposed to be the best. It's very statistical, so I'm not going to get into it. Anyone with interest can please read it up. There's another assumption that we make in survival analysis. We already spoke about proportional hazards. Now, this is something called non-informative censoring. So when we say patients are getting censored, we assume that the patients who are getting censored have the same survival prospects as those who are continuing in the study, okay? And that the reason for censoring is not related to the study. Let's see what this means. So this is a hypothetical study comparing a treatment versus placebo. Blue is the treatment arm and red is the placebo arm. And you can see that in this study, the treatment is obviously doing better than the placebo. In both arms, some patients were lost to follow-up. So this is the original graph. Now let's look at scenario 1. Why are patients getting lost to follow-up? In scenario 1, patients are not coming back to you because the treatment arm has improved so much because of the treatment that you're giving, right? That they don't need to come back to you. And the placebo arm has just worsened and probably died. Now, in the same graph, if you were to incorporate this finding, this data, your graph would actually look like this. The gap between the two arms would actually be much, much wider, which means in this data, you have missed the true efficacy of the treatment because you did not know the reasons for follow-up. On the other hand, there could be another scenario. Maybe the patients on the treatment arm are not coming back to you because the treatment is so toxic that they are either moribund or they don't want to comply or whatever. While on the placebo arm, they are naturally done well and they don't feel like coming back, right? If this is the true scenario, then your curves would have no difference between them. Okay, the treatment has no effect. And this is again getting missed. Now, both of these are obviously very extreme situations just to drive home the point. But the point here is when patients get censored, we assume that the reasons for censoring, lost to follow up, are not related to study participation. So if somebody is leaving the study, it's not because he's feeling so good and it's not because he is so toxic. It's just random reasons. He moved out of the city, he didn't like you, whatever, right? If censoring is informative, that is, it's related to participation in the trial, either toxicity or effect, then it gives biased results. We just saw 2 examples of that. How do you get around this, right? When somebody is lost to follow up, how do you know why he left? There is no way of knowing it. And that is why you need to limit losses to follow up to the minimum. Choose compliant patients, explain the protocol so that they're more likely to comply, have a large enough sample size so that even if 20 patients drop out, okay, you still have enough data on the remaining patients to minimize your percentage loss to follow-up. This was my last slide, and this is a summary of what I've gone over today. We've looked at what is time to event data, what is censoring, what is conditional survival probability, how a Kaplan-Meier survival curve is drawn, how we compare these curves using either a log rank test or a hazard ratio, which depends on the proportional hazards assumption. We've just gone over the various oncological endpoints and in which situation you should be using both. And finally, why appropriate duration of follow-up is important. If there are any questions, I'll be happy to take them.
So, ma'am, there are actually 5-6 questions which are not related to Kaplan-Meier. But if your summary slide, if there is a question on survival analysis and a short note on Kaplan-Meier, what would you expect from the answer to be? You know, they can't draw the curve. I mean, they can draw the curve, but they can't explain it the way you did with the probability thing. So, what would you think would be appropriate to have it in an answer?
What you need to know is that survival analysis is needed when you have time to event data. And the reason for this is that many patients will not experience the event before the study ends or will not have complete observations because they lost to follow-up. What survival analysis does is that it uses the principle of conditional survival probability, calculates survival probabilities at different time intervals. It is depicted graphically using a Kaplan-Meier survival curve. Patients who have incomplete observations are known as censored patients, and the reasons for censoring are either losses to follow-up or participant reaches the end of the study without experiencing the event, or the patient has some competing risk. We discussed that. That's not very important. And so if you don't mention it, it's fine. Okay. Survival between two treatment arms is compared using the log rank test. And you can derive a hazard ratio, which tells you what is the risk of experiencing the event in one arm versus the other arm. You could also do subgroup analysis and calculate hazard ratios for different subgroups. You could elaborate on the different oncological endpoints and say overall survival is the gold standard, but in certain settings, it is not a practical endpoint. And therefore, we have surrogate endpoints like DFS and PFS, which are used in the adjuvant and in the metastatic settings respectively. And I think that should be more than enough for a short moment.
Okay. So there was a question that there are different types of survival analysis. So what are the different type of survival analysis other than Kaplan-Meier, and why do we use only Kaplan-Meier?
So as I already explained, there are two main types. One is what we call the Kaplan-Meier or the product limit method. The other is what is known as the actuarial or the something else. It's called the life table method. And we use this because it's more precise. It gives us survival probability every time there is an event. Whereas in the life table or the actuarial method, if you have events in the middle of a time interval, it's difficult to say whether a particular person was dead or alive for that interval, and therefore you'll have to make a lot of approximations. So typically for biomedical research, we stick to Kaplan-Meier, which is the product limit.
So if there are no questions on survival analysis, ma'am, there are a lot of questions on the forest plot. There's some on the odds ratio.
I'm happy to keep going on, but I'm going to, people are free to leave if they don't want to, because it's...
So they keep on leaving. So I'm just thinking, should we have another session where we answer all these? Because, having them with a PPT and slides like you did for the Kaplan-Meier, I think, will that be more helpful, ma'am? I know it takes a lot of your time, but we can do it.
I have a ready presentation, but you just need to tell me what topics you want covered, and I'm happy to do it.
So can we schedule it sometime after a month? Probably, after 4 weeks, we can have another thing, and we'll try to include what we didn't include today, like the confidence interval. We can include the forest plot. We can include the odds ratio. I mean, the more basic ones. Actually, I came up with this topic because I came across a lot of question papers in the radiotherapy and surgery examination. But I think there are a lot of more statistic questions that people have rather than just this thing. So I can...
Happy to do it if you can share a list of topics.
Sure, ma'am. Thank you so much. I hope you... this was the most interactive class. We don't have questions in between usually, but you managed to break the taboo, and we were actually scared. If so many people ask questions, then the flow gets broken. But I think you are used to answering more questions than we asked. So, but before we end, I think we need to thank you a lot for this thing. If you go through the chat box, a lot of people are thanking you. I'm not calling out all their names, but but it's just the reason that ma'am, even now 5 years I've left Tata, but I still remember that plot, and I told Dr. Geeta that I want to see that plot again to revise Kaplan-Meier, and thankfully we have a video recording of this lecture in our archives now, so anytime I can go back and see that plot again. Thank you so much, ma'am.
Thank you.
So there is a little suggestion from me, when you read a paper, so if you could have something practically happening, so you're reading a paper and, there is an odds ratio there's a hazards ratio there, the confidence interval there. So, in relation to reading a paper, if you could, tell us which are the important things to focus on.
Dr. Geeta, I'm going to suggest that you do this in two parts. One, a more didactic one like this, where you discuss
Okay.
what is a risk, what is a ratio, what is a confidence interval.
Okay.
And critical appraisal of a paper, where if you know who your audience is well in advance, you can actually share the paper.
Mm-hmm.
Yeah, we can do that.
Yeah, that'll be wonderful. I think that'll be wonderful.
Yeah. And we'll plan this next month. So give us 4 weeks, we'll do that. So,
So 4 weeks for the didactic lecture and maybe another 4 weeks before we do the paper thing.
yes, whenever Madam.
Sure.
So, so we need to tell the quiz answers, and Dr. Geeta is being our quiz master, and she's keeping a tab on the answers that people have sent. So, ma'am, stay on for the answers, please, because
I need to know.
might. Sorry.
I need to know some of the answers.
No, you know all of them. I just made up the fifth one. Otherwise, I'm sure you know all of them. So, Dr. Geeta, can you tell us the how many people participated in the quiz and?
So I thought, this quiz is going to have very few people participating, but fortunately we've got 13 people who participated, and we have 3 people who got it all right.
Let me give the answer first.
Yeah, you give me the answer and then
okay, sure. So which of the following survival parameter is the gold standard for assessment for an intervention in non-metastatic setting? And as Madam told, it is overall survival, and she really gave an example of Dr. Ian Tanuk's talk, which I think you can keep it as a flag in the mind that he had said that either live better or live longer, and overall survival is something that we need to keep in mind. Why I use the word non-metastatic setting is because what I said that in a metastatic setting, OS might not be the best answer. You might have to look into PFS, and that is what was the second question. Which of the following survival parameter is not applicable in metastatic setting? And the answer was disease-free survival, because as Madam said, the disease-free survival means that clinically and radiologically there is no disease, and in a metastatic setting there might not be a condition where you will actually get a disease-free survival. But I still put it as the best answer because there might actually be a time where you could have complete response. So, but of all 4 options, third was the best answer actually. Which of the following is not an example of survival analysis? So, fertility model is something which I came across today when I was looking for questions. And fertility model, it explains is something that we look to evaluate multiple events at multiple time intervals. So what Kaplan-Meier does, it just calculates for one event. It does not do for multiple events. But fertility model, it says, I have not read it, it is just search that I did. So the answer is that all these are type of survival analysis. So the answer is fourth or none. Okay, so censured event during Kaplan-Meier censured event during the study in a Kaplan-Meier include all except, and it includes a defined event happening after the study period. So anything will lead to event or all of these: subject dropout, loss of follow-up, or a defined event. And the fifth one, which software cannot be used for Kaplan-Meier analysis? So SPSS, Sigma Plot, and Origin Pro are all can be used. Ecamm Live is a live streaming software which I am using actually to bring this live to you. I couldn't come up with a fifth question, sorry. So that is why this fifth question. And Dr. Geeta, now the answers.
Okay, so like I said, 13 people participated,